Hello everyone. Today we are going to talk about autonomous driving vehicles and reinforcement learning in Unreal Engine. This is my first YouTube video and I decided to record the presentation of my work since I saw on YouTube a lot of people interested in the topic and looking for the source code. The source code of this project, as almost all my other projects, is available for free on my GitHub page and I will leave you the link below. Feel free to clone it, make changes, make pull requests if you want, and if you find it interesting, leave a start to the project. Some background information about this project. This is a project that I did some years ago for a Chinese university in collaboration with my hometown university. Some information about me. I'm Maurizio Vassallo, I'm from Italy. At the moment of the presentation, I was doing a master's degree in data science engineering. And right now I'm a PhD student at the University of Liège in Belgium. A brief overview of autonomous driving vehicles. The definition of autonomous driving vehicle is a vehicle that can drive without human intervention. They are expected to be the future since they predict to fulfill all mobility needs in the next years, and a lot of companies are investing in these vehicles since they expect a huge return of investment. Some of the main advantages of these vehicles are safety. More people could access this vehicle, for example, all people without a driving license. They improve the city space management and reduce the emission thanks to the smart acceleration-deceleration systems. What makes these vehicles smart is the huge number of sensors they are equipped with. For example, cameras, lidars, radars, and so on. And since this is a lot of information and it is difficult to process in an analytical way, usually artificial neural networks are used. This project focuses mainly on reinforcement learning, so I will briefly explain what reinforcement learning is and its main concepts. Reinforcement learning is a machine learning training method where an algorithm learns with a trial and error approach. At its core, reinforcement learning involves an agent that is the decision-making entity that receives some information from the environment, the state, and chooses an action. This action is applied to the environment, and the environment gives the agent new information, that is the new state, and a feedback that can be a punishment or a reward based on the outcome of the action. With this feedback loop, the agent learns and adapts using the past information to infer its future decisions. At every loop, the agent tries to maximize the reward he gets and minimize the punishment he receives, making reinforcement learning a suitable tool for training smart agents. Why reinforcement learning? Because it has gained a lot of popularity in the last years, thanks to the results they obtain in different fields, for example, self-driving cars, games, finance, and so on. Now I will go into the details of the project implementation. I don't really like the slides, because goals and objectives, what is the difference? And also the goals are at the end of the slide, they should be at the beginning, so don't make my same mistake. So the goals of this project was to train some models and perform which one is better. And the different steps were building the environment, set up the actor, and write the code both for the client and the server. And the main tools were Unreal Engine for the environment, Blender for building the trucks and for the programming languages part, C++ for the environment, and Python for the machine learning part. The agent of the project was a car that is taken from the asset store of Unreal Engine for free. It is a physics-based car, so it has mass, it has gravity, can accelerate, decelerate, turn left, turn right, and so on. The environment is where the agent lives, and there are mainly two tracks, a simple one that will be used for training purposes, The idea behind this track is that the agent can learn in a simple track, so it will learn in an easy way. And this track is run clockwise and counterclockwise, so the agent will learn to turn left and right depending on the position. And there is another track that will be used for testing purposes, so the agent will be trained on the simple track and test on the complex track. The state is the information the agent receives from the environment, and for this case there are 32 LiDAR sensors spanned over a 170 degrees angle, and this is a boolean these are boolean values, so 0 and 1. 0 for the red lines, that means that there is an obstacle, and 1 for the green rays, that means that there is no obstacle. The agent can decide one of 5 actions, so the action space is discrete, and the agent can turn left, turn slightly left, go forward, turn right, or turn slightly right. To explain the reward function, I have to introduce an angle, that is theta. That is the angle between the forward direction of the car, that is the blue ray, and the vectorial sum of all the green rays, that is the orange line. And without going too much into details, the reward function is proportional to the number of green rays and this angle theta and the speed of the car. The policy is how the agent chooses an action given a particular state. To find the optimal policy, there are mainly 2 phases. The first one is exploration, so the agent chooses random action to explore the environment, and then he uses this knowledge to exploit, so choosing the best action depending on that particular state. And this is known as epsilon greedy strategy. And there are 3 main models tested that are DPQ network, double DPQ network, and dwelling double DPQ network. The main difference between the networks is how the current value and the next Q value are calculated. In particular, for the DPQ network, there is only an artificial neural network that is called the policy network. And this is the architecture. It's possible to see that the input layer, there are 32 neurons that are the 32 LiDAR sensor input. There is an hidden layer with another 32 neurons and an output layer with 5 neurons that are the possible actions. The output of the neural network are Q values. You can imagine a Q value as the value of the current state given a particular action. And for the DPQ network, both the current Q value and the next Q value are calculated using the same network. That can be a problem, and since the training could not be stable. So to solve this problem, another network was introduced, that is the double DPQ network. In this case, there is another artificial network that is called the target network that has the same architecture of the policy network, but in this case, the current Q value is calculated with one network, that is the policy network, and the target value is calculated with the target network, and this should stabilize the training phase. There is another network that is the dwelling double DPQ network that has a more complex architecture, but basically in this case the Q value and the target Q value are proportional to an advantage value that is the relative measure of the importance of each action. Now I will go into the results. This is the run with a DPQ network, and it's possible to see that the reward is increasing over the time, the episodes, so the agent is learning. The solid line is the mean of 5 runs, and the shadow region is the 95% confidence interval. Similar for the double DPQ network and for the dwelling double DPQ network. Now, comparing the different results, it's possible to see that all the three models learn to achieve good results, but in particular the dwelling double DPQ network got a higher score. Here there is a table that summarizes the results, and in particular it's possible to see that the dwelling double DPQ network performs better than the other models. And these are the results in the complex track. So again, the dwelling double DPQ network performed better than the other models, but it is expected since this network is the best version of the other networks. Now I will show a little demo of the project. It's possible to see some information on the screen. Epsilon equal to 1 means that we are not taking random actions, but we are exploiting the knowledge of the agent. The reward is the instant reward the agent gets. The cumulative reward is the sum of all the instant rewards. The average speed is the average speed of the car. The number of steps is the clock time steps. And the angle is the angle theta formed between the forward direction of the car and the vectorial sum of the green rays. It is possible to see that the agent turns right and left depending on the state is in, and is driving quite well. So I will fast forward. Around here it's possible to see in the next few time steps possible to see that the agent is a bit confused and he does not really what to do. It goes zigzag, that is not optimal, but he is still able to get on track. Again, fast forward. And around here the agent turns takes the turns too tightly, so he hits the wall, ending the episode. Now some of the future works. Maybe find some better hyperparameters, execute more runs to find more accurate results, set up a real robot, so transfer from the digital world to the real world, and use different sensors. Of course, this project was not state-of-the-art. Usually state-of-the-art are using many sensors for like cameras, lidars, and many other sensors. And this was like a toy example. And also test other reinforcement learning algorithm, for example, the deterministic policy gradient, that can handle continuous action space that could be more suitable for autonomous driving vehicle. Thank you for your attention, and leave a like if you like this presentation, and feel free to write comments in the section below, and thank you again.